Hello folks, so welcome back. I didn't do a tutorial in like freaking ages. This is not going to be a tutorial, right? It's just because I just started with Unreal. I just want to share what I learned and mostly have some feedback from people that actually know how to use it, um, how to do that better, right? So also, I'm recording this on a 4K monitor, so the side, the actually of the UI are going to be pretty small. But luckily there shouldn't be much of here, right? I tried to reduce the resolution to make it bigger, but the screen recorder still recorded the full thing, so basically I just got black bars on the side and didn't help at all. I could record on my second monitor, but it's right on the it's all on the left. It's highly uncomfortable, so let's try to see how it goes. There shouldn't be much to do in the actual um, UI here. Most is going to be in the blueprint, which I can zoom in, so it should be seen visible properly, right? So what are we going to see? So I just, as a first test, I wanted to make something, right, to work, to learn a little bit Unreal, and I want to do something with blueprint. So I said, okay, let's try to do something where I can use some basic uh, linear algebra, some vector math, matrix math, right? So aiming to stuff. So I came out, I'm playing Overwatch, I like it, let's do a Torbjörn turret, right? So I found this model on Patreon for the turret, and that's why I cannot share the projects, sorry guys. Or actually I can share it, I would just remove the geometry, because you need to be on Patreon to have this geometry. With that said, uh, what I did is just animating directly the transform of this geometry, which is actually a compound geometry. So if we go into the geometry, you see I spit it out as three different objects, right? So we have a base, which doesn't do anything. We have a hinge that basically just twist, and we have a turret head, which basically aim, right? So let's see what we get. So this is all done in Blueprint. Next part of the tutorial, we're going to do that using C++. So you see when the ball gets out of the volume, it stops shooting, then it goes back to shooting, right? So there's no animation in this, no skeleton or anything. I did the animation of the barrel is procedural and animating the barrel directly. So let's try to see how I did it. So I said before, I exported the different parts separately, and then I created a new blueprint, right? So I went to blueprint, new blueprint class, and here we are. So I started by dropping in the different geometry, and you can do that by you select the actual geometry you want, right? So let's say the base. Then you do add component, and let's see where it is. It should say mesh or something. Of course, I lost it. There we go, static mesh turret base, right? So if you do, it's gonna add another one, then you place it where you want it, and so on. So I did that, I offset the different part of the turret to be in place, right? So you can see the actual offset we have are here, and these are actually the offset that we are going to use uh, in the blueprint itself. So again, that's not the proper way to do it. You probably want to do that with a proper skeleton, proper rig. I just didn't want to do it. I didn't want to put too many variables into play, so just wanted to say, okay, let's do a simple thing. Let's get on with it, right? And then we move to the actual graph, and that's, whoops, that's what it looks like, right? So there are major, like 6 major parts, right? But the 3 most important one are those 3. So here we are aiming our turret, right? And here we do left and right procedural animation for the gun, right? For the barrel. So we'll go through this and try to figure out what it does. I won't be building manually just because like I will probably make tons of mistakes and it's not any useful for you to see me struggle and try to plug, right? Um, and wire nodes together. So with that said, let's get started. So I will try to focus first on the 3 main parts, actually 2. So aim, the math of aiming the matrix, the aim matrix, and the procedural animation of the gun. This is the same. Probably should be a function. I know there is a way to do it, but it's pretty much exactly the same. It's just offsetted, right? And this stuff is just basically, this is basically defined if you are inside the volume, if you want to shoot. This is basically, okay, we are not shooting, let's interpolate from where we left, because the ball left the volume, to the rest position. And here basically we decide what to do, if we want to interpolate back or actually aim. But let's start with the actual aim, right? So I created a new variable, which new var is not really a useful name, so we can actually rename that. Or actually no, because, let's do it. So aim at, right? So we compile, let's see if everything still works. See now that the ball enters the volume. So no, it doesn't, because it lost, we changed the variable name, and the variable is a public variable. We can see here, the eye is open, so it means it's public, it's something you can set. So we need to go here on our blueprint, and here aim at, we need to reset the actual object we want. In this case, is aim blueprint, right? And we can look at that, what it does, but basically just a blueprint, they use a cosine to move, right? So a waveform to move back and forth. So now let's see if we fix the scene. There we go. So we are back where we started, right? So basically this is the target we want to start at. And you just create a new variable. You click here, you do new variable, you change the type, right? I think it's pawn. Or actor should work fine. What type is it? Yes, it's a pawn. Yes, it's a pawn. Right, sorry, it was not capitalized. So let's see if I do this. Pawn. It's not showing. That's interesting. That's just making an array. Object types, actor. So pawn should be here. Scroll, scroll, scroll. Pawn. Oh, come on. Pawn, here we go. And so it's a pawn, right? So that's how I make the variable. And you see the actual our old name is there. So that's how you make variable, and you make the type you want, you can rename them. So this is the object we have, right? So we are going to do is we get its location, right? And we are also gonna get the location for our actor itself. We are inside the turret, right? So get actor location self, right, is the turret itself. You can do that by just typing get actor location, right? By default is set to self, right? Or you can do get actor, sorry, location. It should be also if it's not in, sorry, if it's not in its set, you just plug the actor you want, right? And they will do the job. So basically here we grab the two position of what we were aiming at and our current position, and we build a name vector, right? So basically we subtract the position of where our ball is to our current position, and we get a vector, right? Now, with this vector, we are going to do two different things. Because if you see here, right, let's actually go to unlit, it's easier to see. We have different pivots here. So on this here is twisting, and here is aiming up and down, okay? So we want to split the rotation doing this, and that's what happens here. So here we compute the up and down. So basically our turret, sorry, let's say in the graph, so our rotation like that. In the other, we compute the twist, which is basically this, right? So I build the hierarchy, you can see that. So basically the turret base is the parent of everything. Then we have the hinge, and then we have the head, and then we have the barrel, right? Oh, so these are not doing anything anymore, so I should probably delete them. Also, turret is not doing anything anymore, and we also have a box, right? So the box is basically the volume that we are going to use, but that's useful later, right? So let's move forward, and let's dive into the meat of the thing. So those are the two most important things where the math is, right? So let's start with the up and down rotation, right? So we go in, and see, it's not that complicated. It looks complicated, but it's not. So basically, we want to see how much up and down we need to aim, right? And I'm going to use Paint to show my awesome drawing skill. I'm using a mouse, so you guys need to endure the pain of my drawing, but hopefully we'll get the point across. So our turret is here. Let's make it bigger, right? Our turret is here. Here is our sphere, right? So we got this vector. So this is our aim vector, right? So we want to know how much we need to move up, right, from this vector. So basically, we want to find this angle, right, the angle alpha. So in order, let's call it this the vector x, right? So we don't have the vector x, and we are going to do that in a brute force way, where basically you are just gonna kill the vertical component of the up vector, right? So we are going to kill the z component, and we are just gonna basically get this vector, right? There is a better way to do projection on another vector, just the dot product, basically, to know how much you are projecting. But here, again, I don't want to do a production-proof tool. It would just make the thing more complicated. You have extra edge cases to check, right? So what I'm going to do is I'm going to make the math that works, like without worrying about too many edge cases. I will explain what the edge cases are and how you can handle them. But for the most of it, I'm going to keep it simple, right? So basically, this is what I'm going to do. Once we have that, you can take, oh, sorry, the arc cosine, oh, that's horrible, basically of the dot product, right? And this will give you your alpha. So basically, we want to do a dot x. Dang, my drawing is really horrible, but trust me, with a tablet, it doesn't get any better, and that's really frustrating. But anyway, so that's the deal here, right? So that's what we're going to do. So we are going to break our vector so we can access the single components, right? So we have our in vector and our second vector, which, if you remember, our vector A, actually, I plugged twice the same vector, doesn't matter. So we're going to break the vector. We just grab x and y. We make a vector, basically, so we build from different floats. And you see z is equal to 0, right? So now that we broke this vector, we are going to normalize. So we built our vector. Basically, that's our rough, horrible projection. And this is our basically input aim vector normalized. So basically, the way we have the two vectors here, just the way Unreal collapsed this node, because we can bypass this and just plug this right away. It will work anyway. That's just how, when you create a macro, you see it's called a macro here. That's how Unreal handled it. So I'm not gonna touch that. So now we have the two vectors which are normalized. So probably I should actually say that in my form, and in my formula, that those one needs to be unit vector, right? And by unit vector, I means that the length of A, right, is equal to 1. And that's basically the process of normalizing. Basically, you divide by the length. But that's not a vector math tutorial per se. So that's what I'm going to say about it, right? So now we have the dot product. So that's known here as dot product. Again, you can just do dot product. Here we get it. That's the same node. Once you plug it, it will look like this. Then we extract the arc cosine, and we convert radians to degree, because arc cosine returns radians. And then we're going to make a rotation. In this case, in order to make it work, we need to plug the value into roll. So we need to rotate on X, right? Which is this. All right. Excuse me. And then we return the value. So now we compute our rotation app. So we know we are spitting out a rotation, right? And ignore this. Basically, what we're going to do here, we are interpolating between our wanted position, or if you are in rest pose, we are going to that position, right? So for the time being, ignore this. Now what we want to do is basically build a transform out of that, so we can set the actual transform our objects. So we want to keep the same position, and we want just to set the rotation. So we are going to get a relative transform. We are going to break it. So we grab our just the location, and we build a new transform with that, which basically is going to be rotation and location. Once we have that, we are going to use a set relative transform, which you see is the turret head. Okay, and we set it, and we're good to go. That's how we handle the head. Now, this is not exactly precise. It's actually going to aim slightly higher, and the reason for this is our head, right? But the head is rotated from this pivot, right? And actually, we're actually grabbing the actor itself position, which is even lower, right? So we are grabbing this angle, which is slightly bigger than this angle, right? So it's going to aim slightly higher, but again, I wanted to keep it simple. I don't want to make a production-proof asset. I just wanted to, because you wouldn't do it anyway this way. I just wanted to make something with a rail. But anyway, let's move forward. So now we want to compute the twist. So let's go into the twist. It is slightly more complicated because I just did it in a different way. I built the full matrix out of it, but that's no big deal. So for the twist, it's similar in the same way, but now here we were looking at the turret from the side, right? Now we're going to look from the top. So this is our turret. Here are the two barrels, and our ball is here. We want to figure out how much we need to rotate in order to aim here, right? So that's the same exact concept. We could do that with a rotation like that, but we're going to do slightly different. So what we do is, okay, we reproject the vector down, so we know on the plane xy what our vector is. So in this case it's here, and we're going to build a matrix out of it. And how we do it is we build an orthonormal matrix, and to do that you need to use the cross product, right? So the cross product, what it does is, let's say you have two vectors. So let's see, here we are in 3D, right? So I'm trying to build it in 3D. So that's our coordinate system, something like that. Horrible. Right? So those are two vectors. This is our aim vector. This is a given up vector, which is just the straight z vector. If you do the cross, you get a perpendicular vector to those two. Based on the order you do, you can get either this up vector, this perpendicular vector or the other side. So it's up to you to be careful which one you get. So once we have that, we just build a matrix out of it, and we build a rotation out of this matrix. So in this case, we should get a matrix like this. And don't worry, we're going to redo that exactly into code as well, and will be easier to see the actual manipulation we do. Right, and then we have the up vector here. You can see it's coming out straight out of the screen. So let's try to do this. So as usual, we break the vector, we kill the the vertical component, and we normalize it. Then we have a variable, which is the up vector. We can see here is a variable of type vector, and is the straight z-axis, right? So we cross, and we get the first normalized vector. Now, in order to make 100% sure that you get an orthonormal matrix, what you want to do is cross again with the aim vector and the cross vector you just obtained. And let me explain you why. So let's say this is our up vector, right? and this is my aim vector. If we just grab the cross, something like that, I don't know, right? This is not an orthonormal matrix. Orthonormal matrix means that all the angles between the vector are 90 degree, right? This case is not. This is 90 degree also, but this is not. So what you do another cross product with the aim vector and the cross product you just computed, by definition is perpendicular to both. And by crossing, you will get this vector. So you get a new up vector, and then you have that is 90 degree. That's 90 degree. It's horrible, but I hope you get the concept, right? So that's why we do the double cross product. We normalize the vectors and we build a rotation out of it, where we use the aim vector as a forward, so basically aim. Then we use the normalized vector, first cross vector as right vector, and then the second time cross vector as an up vector, right? So we just build an orthonormal matrix, convert it to rotation, and we spit it out. And then you will see we have the same behavior here. Forget the interpolation for now. We grab the local position of the hinge, we extract the position, we build a transform, we set the transformation for the hinge. That's about it. So at this point, our turret is saving correctly, and we are good to go. What's the problem? The problem is, as soon our ball enters the volume, it's going to snap right there, like instant, boom, right? And that's not good. It's not pleasing to see. So basically what we want to do is we want to aim, so as to interpolate to that position. And the way we can do that, the way I did it is this. First of all, I want to know if I should shoot or not, right? So basically I want to know when the ball enters the volume. In order to do that, we use two events: event actor begin overlap, event actor end overlap. Those two nodes are actually not used. We can probably delete it. It was left from experimentation. So when we enter, we're going to set a Boolean value to be true. So shoot, we're going to set it. When he enters, we're going to set it to true. You see the checkbox is in, so the value is true. Instead, when we leave, we're going to set it to false. All right, and that's the only thing it does here. Then we're going to use the event tick here, right? Basically what's driving everything. And we have a branch, so we're going to check, hey, should I actually shoot or not? If we are shooting, if we need to shoot, you see we are going back to the aim matrix. If it's false, we are going back to basically interpolation from the current position to the rest pose. But then we're going to worry about this later. So let's complete our aim matrix. So we are here, we know we need to shoot. Here there is another check, basically make sure that our object is valid, otherwise we don't do nothing. If it's valid, we are going to proceed. So the way I decided to do the interpolation is, Unreal lets you interpolate rotation, you can see it here, and requires an alpha value between 0 and 1 as a usual interpolation. So basically, it tells you how much of the different rotation you need to get. So I created two variables to achieve that. One is a value holding how much we are interpolating right now. Okay? So how much we should interpolate. So that's the value between 0 and 1. Then we have a step. All right, so basically we are going to add this step each time we evaluate, right? So basically it's how fast we are adding it. It's a fixed time step. It's not the best way to do it, but we get the job done, because basically this will change the speed based on the frame rate. If the frame rate is faster, you will see the turret aim faster or slower. But again, rather than using a variable time step, which is not that much complicated, I decided to go for the simplest way and keep a fixed time step. So here we are going to add the step, the delta interpolation. We are adding it, and then we just clamp it, right? Because we don't want to go above or below 1, right? So we just clamped 1 between 0 and 1, and we set our variable equal to that one. In code, that would be current iteration plus equal step. That's all these nodes boil down to a single line of code. And then we are going to use this interpolation value, right? To interpolate between the 0 rotation, because basically that's our rest pose. You can even expose that as a variable, but for the time being, I just want the 0 rotation. And our computed pose, right? And if we print this, actually it's going to be a pain to print. No, it's not too bad. So let's do print string. So let's plug this here. So we're bypassing the guy. And let's print this. So let's see what we get. So we compile, we save, and let's run again. So now it should print. So you see the value boils all the way down to 0. Sorry, from 0 to 1. It's really quick, but you can probably see that here. Oops. There we go. So it's pretty quick, but we can make it more obvious if we reduce the time step. We can actually do it. So that interpolation, let's make it 10 times lower. There we go. Compile, save. So you see, it's increasing all the way to 1. In this case, it doesn't go all the way to 1 because the ball leaves the volume earlier than that, but you now get what it's doing there. So there we go. So we just interpolate, and we do the same exact things for both rotation. We interpolate, so we have a smooth transition between rest pose all the way to 1. All the way to the actual aim of the thing. And you can make also that it doesn't shoot until it's perfectly aimed, but that's again, is extra thing making nicer for production. We don't care about that right now. Instead, if we are not shooting, we shouldn't shoot, we want to go back in rest pose. And the concept is exactly the same, but the reverse. So we have the value that most likely is in high bound close to 1. So instead we want to subtract to this value the delta step, and we clamp it between 0 and 1, and we use that value to interpolate, right? So if before our value was going to 1, when the ball leaves the volume, is going back to 0. So interpolating back. So the only thing we need to do, we grab the current rotation, we interpolate with the 0 value, we build a transform, and we set it back, right? That's the only thing we're doing. Same exact thing here, right? We extract the rotation, we interpolate using the interpolation value we computed, build a transform, and set it for both the hinge and the head, right? So we cover pretty much everything. Our turret is working fine. The only thing we are missing is the procedural animation, right? Now, before moving forward, let me just stress a couple of things here, right? Our projection is not completely accurate, right? Actually, if you rotate the turret, most likely the math is going to fail because it's kind of hard-coded. We projected on a default plane. Like, for example, when we projected on the ground, that might not be the correct thing because our turret might be upside down, right? So might not be the right value. So what you want to do is basically project the vector on a plane, and that vector, so that plane is defined by the matrix itself of the hinge. Let me do that better. So on default, our hinge is like that, right? That's our hinge. Let's call it like that, whatever, that twist, right? But we might have it on the side, rotated 90 degrees. So you want it to twist like that, right? And the matrix in this case would be like this, which this one being the z vector. Instead, here the matrix will be this way, something like that, I don't know. But basically this one is the z vector, so the z vector is pointing left now. So basically you want to point on this plane defined by the other two vectors, right? So that's the plane you want to project on. In this case is this. So here there is perspective, but basically right now this will be the vertical plane, right? So that's where you want to project, and you can do that by just extracting the two vector, project on both of them, and then sum the two projected vector, right? And you would get, so let's say you have this vector right here. So what you can do is project on this one, project on this one, let's say it gets more like this, and then you sum both of those, and you get this vector, right? And that will be your proper projection. And that will hold for every kind of plane, doesn't matter how rotated it is, right? So that's good. The other thing is, I'm rotating on the x-axis to aim up and down, remember? We look at here, but that's not the same orientation we have in the world, so this is hard coded, right? If you start rotating that, we might have some problem. Also, if you are working in workspace, that's a problem. And we could see that actually later better in the C++ version. So you will need to make it more generic. You will need to keep offsets, right? So basically what you do, you compute the aim matrix and then basically you keep an offset, right? Because if we select our tour head, right, you see how it's oriented here, right? So our aim is backwards. Instead, inward is on the side. So you need to be careful. If you grab the aim and then you want to set it as a Y, you will probably flip your matrix. So you need to keep some sort of offset. And this is much more easier with bones because you know what you have. But again, for sake of simplicity, I didn't do that. But anyway, let's quickly check the gun. It's slightly more complicated, but it's not too bad. So what I wanted to do with the gun is this. Basically, I didn't know how to have a set-driven key in my way, right? So basically, I wanted this kind of curve. Oops. A curve that was like that. Oops, actually, let's make it so steep at the beginning and then, oh crap, and then it comes back slower, right? And basically this section is the recoil. So our gun barrel will shoot back, and here it will be the time it goes to rest, to reset position, right? I wanted to do this. I didn't find the equivalent set-driven key until later, where basically I found a timeline where you can add your animation, but I had some trouble with it. I will need to more experimentation, and I already had the procedural animation, so I just kept that. All right. So back to our drawing board. So that's what we want to do, right? So that's going to be our total length of the anim. This is going to be the recoil length, and this is going to be the reset, SRT, RST, whatever, right? So that's what we want to do. And basically I use the isin isout function to do this. And so the whole complex part is basically to figure out in which point you are of the animation, if you're in you are recoiling or going to reset, and then animate compared to that. So let's see how I achieved that. Let's start with the red bar. Doesn't really matter. So first of all, here we have a modulus operation. It's a float modulus, right? Because which is driven by the total animation time. Total animation time is a variable and is set to be 1 second, right? So what basically we are doing modulus 1, and modulus 1 means that we're going to return the remainder of the division. So basically it's going to return us a value between 0 and the total time of the animation. In this one case is 1, so it's going to be a value between 0 and 1. If the animation was for second, we would get a value between 0 and 4. So basically, the value goes all the way to 1 and then goes back to 0, right? Because if it's greater than 1, it means it's divisible by 1, so the remainder will be less than 1, right? So it goes back all the way to 0 and goes 1, 1, 0, 1, 0. So basically, we are splitting the time into section of 0, 1, or actually over our total running time, right? So doing the modulus, let's basically loop the animation. So now that we loop the animation, we just basically want to figure out, okay, is this value greater than recoil time? You see, we are plugging recoil time, which is 0.1. So is the loop of the animation, so where we are in the animation, is greater than 0.1? Sorry, 0.1, the recoil. So basically, we have a value in our animation, and basically we are going to see if it's greater, it means that we are in recoil, sorry, in reset time. If it's less, we are in recoil time, right? And based on that, we want to do two different things, right? So we have two branches. Hopefully it's easy enough to see here. So here we have the recoil because it's less of equal. And below we have the reset time. So let's try to figure out what I'm doing here, right? Here, first of all, I'm computing how long is the reset time, right? And so basically I want to find how long is this, and this is simple to compute, right? It's basically the total animation time minus the recoil time, right? And that's exactly what I'm doing. So I'm doing total anim time minus recoil time. So we know how long it is, right? Now we want to know how far we are from the start of the reset time, right? And so basically, I should probably start clean up a little. Let's do this. So this value here, right? So we have the total time. This value here is just basically the total time minus the recall time, right? So we want to know where in the reset time we are. We do it this way. And that's exactly the same things I'm doing here. I'm doing where we are in the loop of the animation minus the recall time. So basically here we have where in the recall, sorry, reset time we are. So in the case that we are exactly at the start, we will have 0. And when we are exactly at the end, we will have the value of reset time, which we have no guarantee that that value is between 0 and 1, right? And in order to do an interpolation between 2 points, right, basically I want to interpolate between here and here, right, through this point and this point, but it's this value, right? And basically that's the backward position of our gun. I need a value between 0 and 1, so we need to normalize the value we just got. And in order to do that, we are going to use the length of the time of our reset animation, right? So it's kind of like a vector. We are dividing this range for the actual range of the animation, reset animation. So if you clearly see that if we have at the end of the reset animation and we divide by the length, we are gonna get 1. Instead, if we are here, we have 0 divided by whatever value it is, x, but it's going to be 0. So the output value we have is between 0 and 1. We just normalize the range. And then we can use our interpolation. In this case, it's linear. I think I switch it because you see this one is ease out, so we can use ease out as well. You can choose between so many different, so it's up to you. For now, let's just leave it. Linear. So let me just quit Skype. All right. And what I'm going to interpolate? Well, we have two variables declared here, which one is the minimum point and that's the maximum point. That's not a perfect name. In the C++ version, I gave better naming, but basically means we are interpolating between the position of the barrel in rest pose, which is the max, and the minimum pose, so how far back we want to go. All right, so in this case it's 0. And how did I grab those values? Well, 52 minus 52 is the rest pose, and then we go all the way to 0, right? That's how far back we go. And actually back, the minimum is a bit far too back, but hey, we probably don't want to go all the way back here. We want to go minus 26 seems good enough. So we can change that from the minimum to be minus 26. All right. Oops. So basically here, I'm just interpolating using the value I computed, and then basically what we're going to do. So here, sorry, let me rephrase. So here we know how far back our gun is. So that's just one value, the y value in this case. We need to build a vector out of it, right? So in this case, I'm just using a vector in the y direction and multiply and scaling by this vector, right? Oh, that's sorry. No, my bad. So scaling just by this vector. So basically, I'm generating a position out of it. No big deal, right? And then to this, I'm just summing another vector, which is the gun offset. And you can see it's just basically the x and z value that our barrel has, right? They are the same exact value. It's just basically, it will stay in this position. So we are generating a vector which keeps the z and the x, and it's just moving back and forth. That's the only thing we're doing there. So we build it, and then we are going to set the new location of our barrel, and that's about it. Now, we have the branch here, you see, which is coming from our condition here. So basically, this one lets you choose, okay, we want to set the animation we computed for the recoil or for the reset. And here we only show how to compute the reset position, but not the recoil. So let's do that. And the concept is exactly the same, right? So I'm normalizing the value between 0 and 1, and then I'm normalizing between the max and the minimum. So you see the thing is the same, but the order is reversed. So minimum was the first input here, in the recoil is the second. So I'm interpolating from the rest pose to the minimum pose, so the recoil position, right? And I do the same exact thing, I scale a vector, I sum it, and I set it. So this branch, let us just choose which of the two to set. Oh, are we in recoil pose or in relative? We are recoil pose or rest pose, right? So seeing that as a graph might be slightly misleading because it looks like you're computing both paths, but I don't think it's actually doing that. When the code is built, there will be just a simple if statement. So all this will be executed if this is false, and all this will be executed only if it's true. Then we go into the left barrel, which is exactly the same. There is only just one difference. If we see the animation, right, the two barrels are moving offsetted. Kind of hard to see, but let's see from here. So they are not shooting at the same time, which is an effect you can easily achieve. But in my case, I just wanted to shoot them alternated, right? So I'm using an offset variable. Let's see if I can find it. Where is it? Which variable I'm adding? L time offset. Where is it? L time offset. There we go. So that's to the actual input time. I'm just going to offset by a fixed value. In this case, our animation time. Where is it? Total running time is 1 second, so I'm pretty much shifting by half cycle. So this means that when the first gun is in full recoil mode, this one is almost starting. Is about to start shooting, right? So we have alternated shooting, and you can kill the offset, right? We can actually do that. So if I go in the values here, you see all the public variables are here visible. So we can choose how quick is recoiling as well. But let's kill the time offset, and now they should be shooting at the same time. You see, boom, boom, all at the same time. So that's what the time offset does, and that's the only thing changed. All the rest is the same. You can see the graph is the same. We do the same exact thing that we set it. And this is the end of the tutorial. I run through these things fairly quickly, but I will provide the thing. I said at the beginning I could not share it, but I'm just going to delete the geometry. Sorry about that. You can use a simple geometry. I cannot share this geometry, but you would get all this, so you can study that. I try to put comments all over the place, right? But in next one, we are going to actually do the same exact thing. Yeah, don't say, right? But in C++. So we see that the behavior of the third is exactly the same. But all this is not a blueprint. It's a C++ class, right? It's actually this, all this. So we are going through the code and doing the same exact thing in all C++ using the API, right? I like it more this way. So that's it for the tutorial. I run probably too long, too quickly, but I just want to share these things. It's not the best tutorial ever, but hey, that's what you get for being free, right? So anyway, see you in the next tutorial, guys. Have fun.